All right. Everybody can hear me? Good. So when I was 12 years old, I read a story by science fiction writer Isaac Asimov. Probably many of you. I see head shaking. So many of you probably read something by him. He wrote about 400 books and short stories. And in this particular one, it's called The Last Question, and it was set in the year 2061. And there was an energy crisis going on, and so a group of scientists and engineers got together and they put a huge solar collection device halfway to the moon and found a way to efficiently beam this energy back to Earth, and so problem solved. And of course, there were many other energy crises ongoing, and then 5 billion years later, the sun started burning out. So big energy crisis, or could have been, except that by then humans had mastered interstellar space travel, so they moved to other stars. Then 50 billion years later, all the stars were burning out. So big energy crisis, right? And anyway, I won't tell you how it ends. It actually goes on from there, if you could imagine that. And but it has me thinking that there's always been energy crisis, right? I mean, so in the early days of human history, there was probably an energy crisis every day, right? Because the crisis was to get food, so you'd get enough energy in your body to find food the next day, and then there's another energy crisis, right? So it was pretty much every day, and so all really humans needed at that time in terms of energy was about 2,500 kcals per day, which is really only the amount of energy to power a modest incandescent light bulb. So not that much energy requirement just to get the data from day to day and to acquire the food and maybe construct some clothing or some dwelling that you're going to live in. And then fast forward to today, and we use a little bit more energy per person. Actually, we use a lot more energy per person, about 250 times more energy per person. And so, it's not just the food, right? And of course, the food is usually made by somebody else, and it's shipped, and then it's wrapped in plastic, and there's energy in making the plastic, and transporting the food, and making the clothing, and everything else, because we're not doing all of these things ourselves, right? So there's a much more, we're much more free to do many more things because we're not engaged in the daily exercise of getting our own food, clothing, building our buildings that we live in, and so forth. So life is better, but there's a consequence for this in terms of energy, and we should all be aware of that. So how do we get away with this? Well, it's because we are living on ancient energy, right? So we're consuming largely energy that has been captured from the sun over millions of years, and now we're using that, right? It's been stored in chemical bonds, and we combust that or make it into other forms, but we're totally dependent on this, at least at the present. And so let's look at this energy inventory. And so in fact, it really is, if this is actually the total energy use all over the world, not just the United States, but global. And you can really see it's dominated by fossil fuels, coal, oil, natural gas, right? So that's almost 90% of what's used to sustain the world. And you can see then creeping up, right, is renewable, like wind and solar. Of course, nuclear and hydro also kind of complete the portfolio. Now, sometimes I hear people say, I talk to people and they'll say, well, we just need to go, they use an analogy almost like quitting cigarette smoking or something, right? That, well, we just need to go cold turkey and let's just give up fossil fuels, and then, we're forced. Then we have to develop all these other things. But, I think that, if you think about that, we're not just going to give up luxuries. We're not just going to give up the car. We're not just going to, raising the food in our own backyard. If we actually stopped using fossil fuels right now, we'd have to really decide which half of the Earth is going to stop living, right? Because right now, you know, in order to raise the food for 7 billion people, right? The nitrogen. So right now, half the nitrogen in your bodies comes from N2 gas, from the Haber-Bosch process, right? This is a process, right? It's about 100 years old, very energy-intensive process, and so I have this figure because it's really half of our bodies, in a sense, or half of our food comes from this. Another way to look at it, of course, is that we could feed about half the world, and then the other half would not have anything, right? Because there's not enough nitrogen unless we fix it from the atmosphere. And that's a very, very energy-intensive process, right? So in order to make the fertilizer, right, from N2 gas, we need the hydrogen. Right now, mostly comes from methane, from natural gas, and also the large heat and pressure that this process requires. So this is a problem that has to be solved. I mean, if we're going to get rid of fossil fuels, I mean, this is just one of the things, right, that we have to really take care of in order to do that, because there isn't a replacement right now. All right, so I started talking about energy crisis. There's been an energy crisis a lot of people have just really kind of realized. I mean, every president has talked about it since Eisenhower in the United States, right? Because oil and gas production has been going down for a long time. In fact, the blue curve here was predicted by a person at Shell Oil, and then it turned out to come true. This was in the 50s. And you can see the peaks here of both the oil and gas production in the U.S. were around 1970. And then oil, there's been a fairly precipitous decline. And gas, natural gas, it's kind of petered along, but it was down a little bit from that high in 1970. Now, you'll see that I have the arrows 2000 to 2006. And we're now 7 years after that. Well, there's a reason for that. It's because something happened in around 2006 that kind of changed this picture. All right, and that's really made a big change. So and I'm going to attribute it to one person because a lot of people do that. But of course, everything is not due to one person, right? There's always many people that collaborate and contribute to any change in society. But a lot of people give this person a lot of credit for changing that picture. So do people know, anybody know who this is? Okay, his name is George Mitchell. And Texas oil man. And some people call him the father of fracking. And that's because George Mitchell was a guy who operated a lot in northeastern Texas, around Dallas area, not in the city, but outside Dallas. And he was the one who started using some of these newer drilling techniques of drilling deeper, horizontal drilling, and then operating in the shale layer, the Barnett Shale, that was in that area of Texas, trying to extract oil and gas. And there were a lot of people who said, George, you're wasting your time, you're wasting your money, although it wasn't even all his money. I mean, he was getting money from the Department of Energy. But nonetheless, they thought, well, you're wasting your time. Well, it turns out that he wasn't wasting his time, in the sense that after a while he started making a profit. And, as anything in any big industry, somebody starts being successful and making money, then other people say, what is he doing? Let's try to do the same thing. And so really what he was doing was, now we call it hydraulic fracturing or fracking. And just the idea is that it's accessing, deep, rich resources. So, previously most of our oil and gas was coming from deposits that are nearer the surface, and oil and gas that's more pooled up in sort of a concentrated location. And you tap into, I mean, the stereotype, right, is the gusher, right, where you go into the oil and it's under pressure, so it's just spewing out of the oil pipe unless you control it. This is different, because now the shale layer is horizontal. There's many micro cracks, and the oil and gas is trapped within those cracks, right? So, and spaces. And if you just were to drill a well and go into it, I mean, you'd get a small area. You wouldn't really get the money back from the expense of drilling the well. But now by going horizontally and cracking that shale layer, you can extract sufficient oil and gas to make it worthwhile for people to want to do that. So this is the mixture then. So what goes down is not just water to generate the pressure, but also sand, which is used to prop open the cracks. So you want to make cracks, you want to fracture the shale, but then, you know, there's enormous weight right at that depth of the land. You're going to, over time, have those cracks would close up, maybe even very quickly, and then your production goes down. The sand goes in and makes, you know, basically it's a proppant, they call it, because it's really propping open these cracks. And so that's actually, you know, gets into, you know, one of the Minnesota kind of issues dealing with fracking is the sand and the quality of the sand. What you want is a sand that's very hard and spherical, right? Because if it has all these micro spicules, right, you're going to break off, you're going to get fines, you're going to, you know, that's going to clog the pores. You really want to have spheres, or, you know, as much as possible, so that you have spaces right in between those spherical particles. And right, so that's what's happening in Minnesota, western Wisconsin. We have very good sand for this purpose, and so that's become a big issue, right? I mean that this is selling for a premium. There's whole issues of land use and all kinds of political issues, right, dealing with then people's right or ability to sell that sand, and what about people that live nearby and all the truck traffic, et cetera, et cetera. So, you know, so this is getting now into some of the, let's say, the ambiguities or some of the, you know, the conflicting issues dealing with fracking that I'm going to just talk about a little bit. And I thought that one of the best things that I've seen that kind of shows these ambiguities was actually a cartoon that a friend from Germany sent me. So it's in German, but I can, for those that don't read German, I can paraphrase for you. Basically, the devil is, you know, there's fracking water coming into hell, and he's railing about all the things he's going to do to the people on the surface. And I just like this cartoon because I thought it sort of captures some of the ambiguities, right? The devil is against fracking. You know, is that good or is that bad, right? So anyway, so it's really kind of brilliant, I think. The cartoonist who thought this up. So let's look at some of these issues, you know, good or bad. And so this is like what you hear about, right? Because everybody seems to have a strong opinion. If you search on the web, right, is either really pro-fracking or people who just hate it, and there doesn't seem to be a lot sometimes in the middle. But I mean, so these are the pluses and minuses, right? I mean, you know, clearly it's good for our economy, or the oil and gas that we're producing, and we're more independent, right? I mean, there's less we have to buy from foreign countries. There's a geopolitical kind of advantage to that as well. And then there could be an environmental benefit as well, because of the natural gas abundance and price being so low now because of the hydraulic fracturing producing so much gas. There are utilities now that are switching over from burning coal to burning natural gas. And in fact, if we had a complete switch, that would cut the carbon dioxide emissions for electricity generation in half. So that would be very, very significant for the environment, right? So that would be even a net benefit. Now, on the other side, if there's significant methane leaking during the mining, during the capturing it, that could offset those CO2 gains, right? Because methane is a very potent greenhouse gas, even more so than CO2, and so a little bit of leaking methane could actually be problematic. Now, the other issues, and what you'll see a lot, when you go to websites, right, is about the water, contamination of water. People have wells nearby, and then some are complaining that they're getting contaminated. There's a lot, I'm not going to go into detail because, it's all case by case, and You know, there could be, you know, incorrect cases, and then other times where it's true. What we're interested in is the fact that a lot of water gets used, and we would like to see more of that water get recycled, and we would like to see more of the water get cleaned up. So that's where, you know, my research comes in biotechnology, and we think we can potentially make some contribution to that. So let's look at the water. Well, so the chemicals in hydraulic fracturing. Now, a lot of times what people focus in is just the chemicals that go into the water. It's the so-called fracking fluid that goes down. But now we think that you don't just look at that. You have to look at what comes back up, because that's the water you want to treat, you want to, you know, have to deal with. And of course, this water was often in contact with these oily shale layers. And then there's some chemicals that are very unstable that even could break down. Maybe they don't even exist when the water comes back up. So we're really focusing on that water that's coming back up, and you know, what can you do with it? How can you treat it? All right, now I want to give an example of cases where oily water, you know, what can happen, right? And this then sort of underlies our general approach. All right, so you're all aware of the Deepwater Horizon, right? The incident a couple summers ago in the Gulf of Mexico, and I mean, it was tragic and extremely huge and widespread. But there, you know, compared to, you know, what the aftermath, compared to many of the predictions and many of the things you heard in news reports or even from scientists about the damage that would be done that would last for decades, much of that didn't come to pass. And why is that? I mean, why did a lot of beaches a year later look like this? Well, and this review that I cite here is, you know, speaks to this somewhat, is the fact that it's thought that maybe more than 50% of the oil was degraded, and it was degraded much more quickly than anybody thought would happen, okay, by microorganisms that were living in the Gulf of Mexico. So this wasn't really, you know, humans engineering some big biocolumn, and it was really nature largely taking care, although there were dispersants put on that people think did make micro droplets that sped up the biodegradation. But that's really, it was really the heroes are really these guys, the little microbes. And so this is a head of a pin. Actually, both are a head of a pin. One is what you would see, and then the other is on the right is what it looks like under electron microscope. And I just want to emphasize, you know, how small microbes are, and so how amazing they are to, you know, what they could do to this oil. And really the reason is that there were bacteria that were eating oil, and then they were doubling their mass in 20 minutes and dividing, right? So when's the last time that, you know, you ate a 150-pound meal in 20 minutes, right? That's pretty impressive, right? So, so if they can do that, you know, and then two bacteria, then those two bacteria eat some more oil, and they make 4 bacteria, and then 4 make 8. It's exponential growth. You know, you can see what happened in the Gulf of Mexico, and maybe why things turned out a little better than some people thought. There's another explanation, or another sort of underlying observation, is that people, you know, when they saw that the cleanup was going faster than they thought, then the light bulb kicked in, and people said, you know, there's natural oil seeps all around the Gulf of Mexico, and so there are bacteria that were already adapted to eating that type of oil that were already there. Now, of course, the amount of oil was smaller, so the amount of food was smaller. It was just a subpopulation of the total microbial population in the Gulf. But now they're kind of ready, right? They were poised to eat that kind of food, and now they got a big influx of new food. They divided quickly, and hence, you know, good, or at least, you know, reasonable things happened, at least to our benefit. All right, now how does this translate to fracking water? Because it's a different situation a bit. I mean, we're dealing with maybe some oily chemicals, that's in common, but it's much more distributed. We're not talking about, you know, one big body of water, but many distributed. So things like this, right? So here's a fracking site aerial view, and then you can see these ponds. This is the water that comes up, goes into these lined ponds. This is typical of many places, say in Pennsylvania, maybe North Dakota, out in Bakken Shale region. And then so what we want to do is, can we use bioremediation that would be essentially at thousands of sites instead of having maybe this one mega site that nature cleans up. Maybe you need more engineering or more ways to bring in organisms. Now, that might get some people worried, right? Because bringing in bacteria, to do a job and in an open environment, some people might get nervous about that. Take Woody Allen, he said, I really love nature, but I just don't want to get any of it on me, right? So, so you can hear him saying that, right? I mean, I can hear that voice in my head. So I'm sure there's lots of people besides Woody Allen in New York City that are like, you're going to bring in bacteria into the Utica Shale, into the Catskills where we get our water, So, but we have an approach to do this. So, we wouldn't just use any bacteria. We wouldn't use genetically engineered bacteria. And also, we have an approach to sequester bacteria, really, so that they're not really in the water itself, but the chemicals can get to the bacteria, but the bacteria are not really getting into the water. So how would we do this? So this is the approach we're taking. We're encapsulating bacteria into silica beads, or it doesn't have to be a bead. And in fact, here I can even, if you pass that around, you can see. So these just look like these little beads. It's actually 20% bacteria and 80% silica. Don't worry, it won't hurt you. You can probably eat these and nothing would happen. But the idea now is that the microbes are trapped in this matrix. So on the right, it's sort of, and what I'm passing around, right, is the real, what they look like to your eye. And then under electron microscope, you can see that they're entrapped within this matrix. And then on the far left, there's this sort of spongy, right, matrix. And so these pores, chemicals can diffuse in, but the bacteria are now entrapped in this. So what we do is actually mix. It's a silica type polymer. It's a liquid. Then it basically forms around the bacteria. So you can think of it as sand. It's the same chemical material as sand, but instead of putting bacteria on the surface of sand where they'd be clearly some would be breaking off, now we trap them inside the sand. That's the general idea. Now we actually have some experience with this, so it's not just kind of a first-time use. We've also used this in treating drinking water for atrazine. So this has been a longer-term project. We found out this worked very well. There was a startup company out of the university. They wanted to do a test in a water treatment plant in Iowa. They got permission to do that. And so actually, it was a university facility. I mean, they were sold to the company where 35,000 beads were made, and then they plugged this into a sand bed filter at the water treatment plant. And from what we can gather, I mean, it was the company did the test. We didn't do it. So we weren't in charge of the data, but it seemed to have worked pretty well. So we got some good feedback from that about how to actually implement this on a larger scale and how these might be sort of manufactured. All right, now to treat the fracking chemicals, it's a little bit more difficult than the atrazine case. That's one chemical in a very controlled kind of situation in a water treatment plant. Now we're treating on the order of maybe 1,000 chemicals, as many. I mean, if we're talking about contacting oil and there's a little bit of oil in the water, petroleum is a very complex substance, right? Or it's not really one substance, right? It's thousands of different chemical substances. And, the reason it's so complex, I mean, this shows you this is dimethylbenzene, or known as xylene, but even the methyl groups can be in different positions. So you can have 3 isomers. If you have multiple rings, sometimes you get many isomers. So these are some of the structures are very similar, but it's a very complex matrix. And Lisa Strong, postdoc in my lab, spent a lot of time to really sort out the analytical chemistry, so we know what we're dealing with. And also we can test our materials and see if it's really removing as many chemicals and specifically what it's removing. All right, so eating this kind of oily mixture, so it doesn't look too good, right? But I mean, if you have just a little oil and water, it's not quite this bad. But like I said, our bacteria, some of them that we have, you know, they just love this stuff. And some of these have been isolated from things like this, oil droplets in water. And what you're seeing is really black oil droplets, and those white rod-shaped things are bacteria that just glom onto the oil, and they kind of eat it from the outside in. So they're happy. I mean, to them, this is like steak. You know, this is like good steak, right? This is good stuff for them. So what we want to do is figure out how to do this and how to do it quickly, because I mean, it's a pressing need. You know, we're really trying to move this along and really, you know, come up with solutions. So to do that, we're trying to sort of combine, you know, kind of, you know, empirical knowledge and things that have been, you know, learned and what we can do in the laboratory experiments, and also sort of modeling and computational methods that can sort of speed us along, can get us to our goal more quickly. So how do we do that? I'm just going to give you kind of a snapshot of what we do for one sort of system, and then that would be analogous to a body of work that we're doing to approach this. So inside these bacteria are enzymes, right? That's what digests the oil, just like, you know, we have digestive enzymes in our stomach and intestine. So they chew up ultimately the oil chemicals. So this is one of the enzymes for which, you know, it's been very well studied, and there's an X-ray structure, so the atomic detail of this enzyme is known. It's not my work. This was done by Ramaswamy and Gibson at University of Iowa. But we can, you know, learn from and gain from that work. So this is a particular enzyme that really likes aromatic ring compounds. So that's part of the components of oil. So these multi-cyclic rings, that's one of the things that we'd like to break down and get rid of. And it turns out it works on dozens, really, and we'll find out actually even more. But we can actually look at the active site. So we can study this where the reaction is occurring. So it's not really happening that most of that protein is just there to stabilize this active site, which is where all the good stuff is happening. The reaction is occurring. Now, there's been a lot of investment in tools to model what goes on at active sites and binding sites of proteins. And it's not due to biodegradation, bioremediation, but it's due to the ramifications in pharmaceutical companies and drug development, right? Because there, you know, we have a few receptors in the body that mediate things like, you know, hypertension and cholesterol level, right? And if, you know, drugs are usually things that interact with those receptors. And so drug companies spend a lot of time and money figuring out chemicals that bind to those proteins, all right? And so this is one example. You might know of this, Lipitor. So that binds to the protein that is involved in the first committed step for making cholesterol in your body. So you want to have less cholesterol. You bind to that protein, you slow it down or shut it down, and then you lower your cholesterol level. Well, this has been pretty good for Pfizer. In fact, it made them $125 billion. Right, so you can imagine these computer tools are pretty sophisticated. So there's been a lot of effort, not just by Pfizer, NIH, you know, grant money, right? You know, there's been a lot of good, very smart people who have put their minds on this. So we're in a sense tapping into, or we're able to leverage this work that's done for a completely different purpose, but it really is helping us. So now this is binding of one of the chemicals, at least as strong as found in the fracking fluid, in the active site of that oil-degrading enzyme, naphthalene dioxygenase it's called, or aromatic dioxygenase. And the nice thing is, you know, with these tools, he can now test 1,000 chemicals in an afternoon, right? I mean, to do the experiments to do that, line it up, you know, that chemical, and, you know, take us years to do that, right? So we can learn a lot very quickly. Now, we still want to do experiments. We're not just relying on the computer. But, you know, as you gain insights like this, you know, this can help speed you up, develop hypotheses. You maybe avoid going down some blind alleys and so forth. All right, so we take that data. We know computationally or kind of theoretically what chemicals should be degraded by certain bacteria and certain enzymes. And then we do the actual experiment. So we take that bacterium. This is, we gave it our worst sample. I mean, this was from a tank bottom in the Utica Shale where they were separating oil and water. And so this was really oily. It had all this iron sediment in it. It was pretty nasty looking. And then we incubated our bacteria with it in the silica, right? And then over time, you take samples and you start testing, right? Are these chemicals going away? And I'm not going to show you everything because there's about 1,000. But just to give you an idea, then Lisa Strong, what she did was, she can look at now the analytical chemistry, see that some of these peaks are going down. The machine will give you the volume of the cone, the mountain sort of illustrates how much chemical. Then she can plot degradation curves, and we don't really trust, we don't want to do this all manually because we might be biased. So what we do is, we assume that it has to be some first order decay. There has to be a significant difference between the degradation curve and the control before we say it's degraded. And this can all be sort of automated in MATLAB spreadsheets and things like that. All right, so when she does this, we find out that this one organism can degrade about 350 different chemicals. And now we have other organisms that degrade other classes of chemicals. And so, the idea is to cover with a limited number of organisms the full spectrum of chemicals that would be in these different fracking fluids. And that would make it potentially economical, where you could have a sort of a limited inventory that could be manufactured and then used to treat. So how do we learn what bacteria are good? So this is something actually we've been involved with. A colleague of mine, Linda Ellis, has worked many years with me on this database. So this shows this web database where we've compiled information. This is not just from our research, but researchers all around the world. And so we've got to know thy bacteria. That's our kind of commandment here, is we know, certain bacteria degrade certain types of chemicals, and then we can use them. We can do this type of modeling because in many cases, the most well-characterized ones, there's enzymes that are known, their X-ray structure, and then we leverage that information to sort of pick out the right bacteria and use them in the most optimum way. All right, so just in the last couple minutes, I want to wrap up. But just to say, as you can imagine, I mean, there's commercial activity in this area, right? Now, I don't mean just, extracting oil and gas, but now, whenever, in our society, right? I mean, if there's an opportunity for, cleaning up, then and money can be made, then people are going to jump into that. And so this is an article from Forbes just about a year ago, where they were estimating that not the fracking, but even just cleaning up wastewater and hauling, cleaning aspects of the water in fracking could be a multi-billion-dollar business. All right, I mean, it's already, and in fact, I mean, General Electric, Siemens, there's some big players that are actually involved now. Mostly what they do, though, is like industrial scale evaporation or adsorbents, things like this, that really, and so what we think is maybe our advantage or what we could bring is that these other techniques really just concentrate the waste and then you dispose of it somewhere else, like in a landfill. What we're trying to do is get rid of it, right? So to clean the water so that you don't have a chemical somewhere else, you don't, the chemical's gone. So we like that approach, and there might be commercial potential of that. We have funding now from the National Science Foundation. It started in the fall. This is a program. It's called Partnerships for Innovation. So they really want us to work with companies if we can. So if we develop more like platform and academic kind of work with graduate students and postdocs here at the university, but then it's really encouraged in this program that if we come up with things that really work and some company wants to manufacture the beads or really mass produce it, that we would work with them and help them to do that. And that's the spirit, and we're certainly, that's our interest as well. We also have funding from Minnesota Futures Program. It's out of the graduate school office here at the University of Minnesota. And this is actually a little bit broader look at fracking where, like Betsy Wattenberg, Jeff Balicki, I mean, they're interested in looking at, some water issues and toxicological issues and so forth to really look at the big picture. So we're excited, and this project is now ongoing as well. All right, so just in conclusion, I'd like to sort of reinforce kind of one last point, and that's, every projection that you look at for world energy use, I mean, I've looked at, everything from, Sierra Club to Exxon to, and nobody has a graph that's going down, right? I mean that's reality, right? I mean, and so I think we really have to look at things in that context, and that, I mean, if you think about it, the lights are not going to be going off anywhere. If anything, some of these darker areas in Africa, Central Asia, South America are probably going to get brighter in the future, right? So the demand for energy is going to increase. I think people are going to extract energy all different kinds of ways. Certainly, it's hopeful, I think, of the State of the Union address. I'm sure, a lot of you heard last night, here that we'll use, oil and gas funds now to fund more renewable research. I think, that's we all want that. But I think we also have to be realistic that energy use is going to go up. And at least for the time being, there's going to be this, we use everything approach. And so just, one last sort of statement, and I'll let the futurist and writer H.G. Wells make it on my last slide. All right, and with that, I'll thank you and answer any questions. Thank you very much.